Welcome to EDU World Space.
Okay, in problem 92, we have two parts. In part A, we're asked to repeat the derivation in equation 34.19, but this time we have to assume that the lens is immersed in a liquid instead of being in air. And this index of refraction of the liquid is called N, and then we have a subscript of LIQ, but I call it N subscript L because it's much easier to write. And in part B, we're told that this particular lens now is made of glass, which have an index of refraction of 1.6, which I call Ng. In air, the focal length of this glass is 18 centimeters, and I've denoted the focal length in air as Fa. And then we're asked to find the focal length in the liquid of this same glass lens in liquid if the index of refraction of the liquid is 1.42. So in order to tackle part A, what we'll do is, so we have a thin lens, say, I don't know, it can be a converging lens or diverging lens or meniscus lens or whatever. But the main point to note is that it has two radii of curvature, R1 and R2, and these surfaces share an interface with some other medium, right? So this has a particular index of refraction here. For this case, let's call it NB, and then on this side there could be a material that's NA, and then on this other side there could be a material that's NC. So there are two interfaces, one associated with R1 and another associated with R2. Same thing for the diverging lens, or if you have a meniscus lens or whatever. So we'll be applying equation 34.11 for each of the interfaces, while also keeping in mind that the image formed at this side will be the object for the other side. Okay, so, and we're also assuming that the lens is so thin that the thickness itself, or the separation between the two interfaces, is negligible. And that means that the object distance for the second lens is then minus S1 prime. Right, and all of this is given if you read the part where they derive equation 19. So let's continue onwards to rederiving equation 19. Okay, so let's say we're at the R1 interface, and I'm going to apply equation 34.11. So I have 1 over S1 plus 1 over S1 primed is equal to, sorry, that should be NA over S1, and B over S1 prime is equal to NB minus NA over R1. All right, and let's determine what NA and NB are. So NA, this will be the liquid, right? Index of the liquid, which I have called NL. And then NB will be the index of the glass, which I've called NG. So we can go ahead and substitute for NA and NG into this equation. So I have NL over S1 plus NG over S1 prime is equal to NG minus NL over R1. And I'm going to call this equation 1. And now let's look at the interface at R2. Okay, so again, we're going to apply 34.11 at R2. And this time I have NB over S2. So NB is, again, the glass we assume is made of one, the lens is made of one material, which has an index NB. So that's S2 plus, and now the other side of that interface will have, let's say, NC over S2 primed. And that's equal to NC minus NB over R2. Now, NB we already know. NB is the glass, right? Index of glass. And that's NG. And, well, since we're in the same liquid, the light is going to exit into the liquid. So NC will be index of liquid, which is NL. So NA and NC are both NL because the glass is fully submerged in this liquid. And let's remember that S2, this object, is actually the image formed by the R1 side. Okay. And because we're neglecting the thickness of the lens, we have this kind of relationship. So if we go ahead and substitute everything that I box off in the red region, so if I substitute all this red stuff into here, then I will have NG over S minus S1 primed, right? Because I'm substituting of 1 NB, which is NG, and then S2 is minus S1 primed, and then plus NC, which is NL, over S2 primed. And that's equal to NC, which is NL, minus NB, which is NG, over R2. And let's call this equation number 2. Now we're going to follow the same steps that they did in deriving equation 19, and we're going to add equation 1 and equation 2, right? So if I add equation 1 and equation 2, notice that I have a negative NG over S1 primed, and that will be added to NG plus S1 primed. So this factor here will cancel out, and that will go away from my equation. So then I'll have an equation that's NL over S1 plus NL over S2 prime, and it's going to be equal to NG minus NL over R1 plus NG minus NL over R2. So let me do that on the next page. So add equations 1 and 2. And that when I do that, I get, let me see, NL over S1 plus NL over S2 primed is equal to NG minus NL over R1 plus NL minus NG over R2. So here I can factor out NL, and that gives me 1 over S1 plus 1 over S2 primed. And here I can write NL minus NG as minus NG minus NL over R2. And if I do these two things, then this equation becomes NL times 1 over S1 plus 1 over S2 primed is equal to NG minus NL, all of that times 1 over R1 minus 1 over R2. And I get that minus sign because of this minus sign here. And because when I read it like this, I can factor out NG minus NL, and that leaves me 1 over R1 minus 1 over R2 over here. And if I divide both sides by NL, then I have 1 over S1 plus 1 over S2 prime is equal to NG minus NL over NL, and all of that stuff times 1 over R1 minus 1 over R2. And And if you follow now, so this is the new, uh, this is the object and this is the image. So we can do like they did in that and just relabel S1 by S and S2 prime by S prime. And that will give me 1 over F, right? But then the 1 over F can be defined by all the stuff on the right side. So that's NG minus NL over NL times 1 over R1 minus 1 over R2. Now, to make sure that we have the right equation here, if we take the special case where NL is air, right, we had better get the Lensmaker equation. We better get equation 34.19, which tells us it's 1 over S plus 1 over S prime is equal to N minus 1 times 1 over R1 minus 1 over R2. And indeed, if you set NL equal to 1, and then you call NG N, then indeed this equation becomes 1 over S plus 1 over S prime is equal to NG is N, and L is 1, and that's 1 over R1 minus 1 over R2. And that's for sure the Lensmaker equation. With the focal length 1 over F given by N minus 1 times 1 over R1 minus 1 over R2. Okay. So here, this is the main result. This is the result that we're seeking in solving part A. And I just wanted to show you that it was the correct result because it's an agreement with what we have in the textbook. And now we'll go on to solve part B of the problem. And so this is just you plugging in some numbers and just kind of see how this particular problem is worked out when you're given some of the values. So let's do it on the next page. So okay, in part B, we're given that the focal length of the glass lens in air is 18 centimeters, right? So then that tells me that 1 over F A is equal to NG, right? So remember that's the index of glass minus 1 times 1 over R1 minus 1 over R2. So I have this kind of equation, and I want to find the focal length in the liquid, right? That's what they're asking us. So we can write 1 over FL using our previous equation here will be NG minus NL over NL, 1 over R1 minus 1 over R2. So I have NG minus NL over NL, 1 over R1 minus 1 over R2. So let's review the things that were given. So we know FA, we don't know FL, so that's what we need to find. We know NG, they told us that's 1.6. We know NL, they told us that's 1.42. We don't know 1 over R1 minus 1 over R2, but it's common to both equations, right? So that what we could do, so let's call this, I don't know, equation 3 and equation 4. Okay, we can do this in two ways. Either divide 3 by 4 or solve 3 for 1 over R1 minus 1 over R2 and then substitute it into 4. So we can just go ahead and divide. So we have 1 over FA divided by 1 over FL is equal to ng minus 1 over ng minus nl over nl, right? And then that gives me FL over FA is equal to NL times NG minus 1 divided by NG minus NL, and all of that, well, times nothing. And let's move times 1. But let's move FA over to this side. So then I have FL is equal to NL NG minus 1 over NG minus NL, then all of that times the focal length in air. So now we have an equation that will tell me the focal length in the liquid if I know the focal length in air and all the indices of refraction. So then FL, right on space. Let's go to a new page. FL is equal to 1.42 times 1.6 minus 1 divided by 1.6 minus 1.42. All of that times 18 centimeters. And that's equal to 85.2 centimeters. Now, I strongly urge you to go ahead and check the numbers and make sure I haven't made any like arithmetic mistakes or anything like that. But this should be the result that we're seeking.